Hello all you AP cameras out there. Welcome to day one of your coronavirus break. I know this isn't ideal, but hopefully we'll do what we can and make this work. On day one here, I'm just going to push a video out to you about our next lesson, and then we'll try some other things out and see how they go. So I hope you're well. I hope you're well rested, and let's go. So we're going to be talking about reaction rates of reactions again. And as you recall, we had said that reactions slow down over time. And the reason for that is because you're using up more reactants. They collide less often, and so your reaction just can't go. To show this in multiple ways, you can look at a table such as we have up here. This was from your notes from the other day, so it's nothing new. And then we're going to make a little graph of our concentrations over time. You know the general shape is going to be decreasing and exponential. But we'll just go ahead and see what it looks like by plotting some points. So at time 0, we have a concentration of 1, so I'll put a point there. And at time 10 seconds, our concentration has dropped to 0.82, so I'll put another point there. After another 10 seconds, it's dropped, but it's dropped less, about 0.67. After 30 seconds, it's 0.55, about there. 40 seconds is 0.45, about there. 50 is 0.37, about there. And then at 60 would be at 0.3 right there. So as you can see, I dropped a less distance each time because the reaction is slowing down, and so the change every 10 seconds is less than it was the 10 seconds before. If we were to continue drawing this out, it would level off, something like that. Right? So in this lesson here, we're going to be able to actually calculate how fast your reaction is going, calculate what your rate of your reaction is. As you can guess, it depends on the concentration that you have left at that particular time, and so that will be in our equation. And so the equation to calculate the rate is known as the rate law. And to look at the rate law for a generic reaction such as A plus B to C, it's going to look something like this. Your rate of your reaction is going to be equal to your concentrations of your reactants multiplied together. So we're including only A and B because they're reactants, not C. It's a product. The rate of your reaction doesn't depend on how much product you've made, only on how much reactants are still left. But there's some more to it. There's also a rate constant, K, parked out front, represented by the letter K. And not every reaction goes the same rate. Some are faster, some are slower. So your fast reactions will have a larger K value, and your slower reactions will have a smaller K value. And then there's one more thing too. Not only does it depend on the concentrations you have left at that time, but it also depends on the exponent of the concentration. So this is going to be raised to some power. We'll call it m for now, and B will be raised to some power called n. You don't know what these exponents are. They are not necessarily the coefficients from the equation. They're something that you'll have to figure out. And these are called orders of your reaction. It tells you how your rate depends on your concentrations. We're going to see orders of 0, 1, or 2, and that's it. There are other ones out there, but those by far are the most common ones. And of those three, the most common will be first order and second order. So if A was first order, it would have an exponent of 1, and if B was second order, it would have an exponent of 2. Again, we have no idea what those are just by looking at the equation. We'd actually have to do some experiments to figure it out. We'll talk about that the next day. But for now, this is the generic form of rate law. So the rate is the rate of your reaction at a given time. K is called the rate constant, and it's unique for a reaction. At a given time. So a different reaction has a different value of K. As we'll see, it also depends on temperature too. The hotter your reaction is ran at, the larger the K value. Okay. So this is the generic equation for the rate law of a reaction. Your rate depends on your concentrations of your reactants and your rate constant K. Okay, okay, so let's go on and see what this would look like. So that rate constant K, you can read some information there. It is a constant for a given reaction at a given temperature. It will always be the same at that temperature for that reaction, no matter what your reactants are. It's a measure of your reaction's overall speed. The larger the K, the faster the reaction is going to be. As a constant, it does not depend on the concentrations. It does depend on temperature and on activation energy, which we'll talk about later. Do you think a given reaction have a larger or smaller K value if it's performed at a higher temperature? So we said K does depend on temperature, and this would be larger. We know that a higher temperature means a faster reaction, and according to the rate law, if your concentrations haven't changed, if all you're doing is changing the temperature, the only thing that can change in here is going to be your K right here. And so if your rate goes up because it's faster, that means your rate constant is also goes up too. Okay. And so although K is a constant at a temperature, it will increase if you heat it. And this is always true because reactions always go faster when you heat them. There's a little blurb there. We can actually calculate what this K value will be. It's using something called the Arrhenius equation. We won't get into that, but it's kind of interesting if you'd like to check it out. And so let's take a look at a couple samples here to see how K affects things. So we have two reactions with different K values. Both reactions are first order in A and C. You know that because there is no exponent written, meaning that it's assumed to be 1. And so the order of each reaction is first order. And for B, which reaction is faster? If you have equal concentrations of A and B, that would be reaction 2. And the reason for that is because for 1, your rate is going to be equal to the rate constant 10 times A. Let's just say that A is 1 molar initially, so you're going to have a rate of 10. And then for 2, your rate would be equal to the rate constant of 100 times that same concentration of, say, 1 molar. And so your rate's going to be 100. So your reaction 2 is going to be faster because it has a bigger rate constant. So which reaction has a smaller activation energy, 1 or 2? I'll let you think about it for a moment. You can pause. Okay, well, we said for a faster reaction, it's faster for a reason. It's faster because it has a smaller activation energy. If you remember our little diagrams, activation energy is the size of the hump there. The smaller the hump means the more molecules can make it over the hump to become reactants, to become products. And so the faster reaction has a smaller activation energy. Therefore, we know that the faster reaction is reaction 2. So it's going to have the smaller activation energy. So you can see that K is inversely related to activation energy. As activation energy goes down, your K value goes up. So they're all related to each other. So in part D here, 2 trials of reaction 1 performed in the lab. Trial 1 uses 0.1 molar concentration of A initially, and trial 2 uses twice as much as 0.2. Which trial is faster and by how many times? Again, you can plug it into the rate law and see. Hopefully you would realize that more A means more reactant. More reactant means a faster reaction. So you would expect trial 2. So to see how that would work, for trial 1, our rate of reaction is equal to K. Because this is reaction 1, K is equal to 10. And in this case, in trial 1, our concentration is 0.1 molar. And so we're going to have a rate of 1 something, where the something is some unit. In trial 2, our rate constant is the same because it's the same reaction at the same temperature. The only thing that's changing is our concentration, and so you can see that it's going to have a rate of 2 somethings. And so, indeed, trial 2 is faster, and it's 2 times faster. You double the concentration, so you double the rate. Basically, you have more reactants to run into each other, and so they're going to react faster. And then lastly, E, reaction 2 is performed using 0.5 molar C. The extent of the reaction is monitored using colorimeter. As the reaction proceeds, what happens to the concentration of C? C is a reactant, so you're going to use that up, so your concentration of C is going to drop. As a result of that, we said that the rate of your reaction drops as well. And we can now explain this two ways. On the molecular level, we can say that there's less C to collide and react. So reaction slows down. And now we have a mathematical way of explaining that too, because we know the rate is equal to our rate constant, which is constant, times your concentration of C. And we said that C is decreasing. Your rate constant has to stay the same, so something else has to give, so that means our rate is going to be slower as well. Okay, so that's kind of how your rate depends on your rate constant and on your concentrations. The other part of the equation, and the part that's a little bit more confusing, is the order of the reactant, those exponents up there. It tells you how the rate depends on the concentration. And again, our values are going to be first, second, or zeroth order, although others are possible. It is not related in any way to the coefficient in the overall reactions balance equation. Later we'll see where it comes from and how we can figure it out. Okay. There's two ways to find the order. The first is using the rate law, using initial rates of mini experiments, which we'll see tomorrow, and then the integrated rate laws, which we'll see later in the week. But for now, let's just practice each one, see how they work. So if we have a first order reaction, the rate law for this reaction will be the same as for all rate laws. So the rate is going to be equal to the rate constant K times the concentration of your reactants raised to some power. In this case, because it's first order, it's going to be first power. Sketch a graph of A versus time. Say you start with some initial amount of A. It's going to decrease over time exponentially. And we'll get something like that. Okay. And so the rate of the reaction slows down over time. We know that because we have less A. And we can also tell from the graph too, the graph is leveling off and becoming less steep. Which means that the amount of A is changing less and less as we go on, and so it's getting slower and slower and slower. Say, let's try some math here. If the concentration of A is 2 moles per liter, the rate of the reaction is 6 moles per liter minute. What's the value of K, the rate constant? Alright, so let's go ahead and plug this in. And so our rate here is going to be 6 moles per liter minute. We know that's the rate because rate has to have a unit of time in there. For right now, I'm going to work with just the numbers, and then we'll work with units later. K is what we're looking for, so that's unknown. And then our concentration of A is 2 moles per liter. And so you can see there that K is going to be 3. If you like to work out the units are a little funky. I'm going to write the units only and not the numbers. And so using our rate law, we have moles per liter minute is going to be equal to K times concentration in moles per liter. We have moles per liter on both sides, and so we can cross out moles per liter. And we're going to see that K is equal to the only thing left over on the other side, which is 1 over minutes. And so technically the value of K is 3 inverse minutes. You can write it like that, or you can write it as 3 minutes to the negative 1, or however you choose. Right. And so that probably doesn't tell you much right now, but now that we know the rate constant K, we can find how fast the reaction will go for any concentration of A, which could be kind of useful. So if we double the concentration of A to 4, what's the new rate of the reaction? Well, hopefully you realize it's going to be faster. But we're going to just go ahead and plug and chug and see how much faster. So now we don't know our rate, but we do know K is now 3, and our concentration is 4, and so it looks like our rate is going to be 12. And keeping the same units as before, it'll be 12 moles per liter minute, including that factor of time in there too. Okay. And so if you notice, if we doubled the concentration we have also doubled the rate. And this is true for all first order reactions. Whatever you do to the concentration, you'll do the same thing to the rate. So if you double the rate, double the concentration, you'll double the rate. If you triple the concentration, you'll triple the rate, and so on and so forth. Alright, let's take a look at second order reactions. This time we're going to one of my favorites, C to D, and the rate law for this reaction would look like something similar. Rate will equal to the rate constant K times the concentration of C, this time raised to the second power because it's second order. If you graph a rate of C over time, just as before, it's going to be decreasing exponentially. It's difficult to tell, but your slope of this graph should be a little bit steeper than first order. It doesn't really matter for us because they'll kind of look the same, but they are slightly different. Okay, number 3, the rate slows down, just as before. We know this because the concentration of C is dropping, and because our graph is leveling off too and becoming less steep. Alright, we're given the rate constant to be 0.25 moles per liter seconds, and the concentration 1.2. We want to know the rate of the reaction. Mainly plug and chug. I'll let you guys take it from here, and you can pause the video, and then we'll compare answers. Okay, did you get 0.36? Great. The units would be moles per liter seconds. If you wanted to, you could work it out. Or you could just take a look at the units of the rate constant given, rearrange them so the time's on the bottom and concentration's on top, and you're good to go. Usually units aren't such a big deal. Every so often they'll ask for them, but not usually. Okay. Alright, now we're going to double the amount of C, and what will happen to the rate? Obviously it's going to increase. And is it going to double like before? Let's find out here. I'll let you go ahead and work it out, and I'll meet you in just a second. Okay, sure enough, the rate did increase, going up to 1.44 instead of 0.36. But notice this time it did not double. If you're looking closely, you'll notice it quadrupled instead. And welcome to second order reactions. This is the role of that 2 up there. Basically, whatever you do to your concentration is going to have the squared effect on your rate. So if you double the concentration, you're going to quadruple the rate. If you triple your concentration, you're going to non-tuple the rate, and so on. Okay. So this is second order reactions. In first order, if you double the concentration, you would double the rate. If you tripled it, you would triple the rate. But second order, because of that exponent, you're going to square it instead. Okay, those are the 2 most common types, second and first order. Now we'll look at 0th order. Okay. So here we're looking at E going to F. The rate law for this reaction would be, as you probably guessed, rate equals K times the reactants to the 0th power. Anything raised to the 0th power, of course, is 1, and so this simplifies to just K. And so this is kind of interesting, because the rate of this reaction does not depend on your reactants. It's always going to be constant, no matter how much reactant you have. So these are kind of rare, but they do occur, especially if your reaction is catalyzed. Typically, it depends on how much catalyst you have. The reaction won't occur without a catalyst, and so you're kind of waiting on the catalyst to bond with the reactant to make things happen. And so in this case, your reaction is going to produce a downward E graph again, but this time it's going to be linear instead of exponential, because the amount of E that's changing is the same all the time. And so here the rate of the reaction is constant because it doesn't depend on your reactant. And we can tell that also from the graph, because the graph always has a constant downward slope. It's always dropping by the same amount, no matter how much E you have left. Right? Okay, so we can go ahead and do some plugging and chugging. Go ahead and work on 4 and 5, and we'll meet up here in just a second. Okay, we're back. As you can see, this is probably the easiest math you will see in here all year. The rate is going to be 1,200 molecules per minute, regardless of how much E you have. And that's going to be your rate constant then too. So, pretty simple math there, but unfortunately they're not very common. Now, what do you do about reactions at multiple reactants? Well, you write a combined rate law. And so let's go and try this out here. The rate law for this reaction will be rate is going to equal the rate constant K times the concentration of each reactant multiplied together raised to some power. And so in this case, we know that G is first order and H is second order. And so our rate law will look like this. And that's all there is to it. For 2, we're given the concentration, so we can go ahead and figure out what our rate constant is. We can plug and chug. And then number 3, we're going to change those concentrations. And so again, you can pause your video, work those out, and we'll meet in just a second. Okay, here's my answers. I got a K value of 800. You can work out the units. I'll skip those for now, though. And then we can use that value of K in number 3, where we're doubling both concentrations, and I got an answer of 6.4 moles per minute. We can step back and see if this makes sense. Let's see, by doubling G, what effect would that have on the rate? Because it's first order, that should double the rate, so congratulations. That's 2 times what it was before. And then by doubling H, because this is second order, doubling it actually quadruples it. And so we have 2 factors here. Doubling G doubled the rate and doubling H quadrupled the rate. You put them together, you get a reaction rate that's 8 times what it should have been before. And before it was 0.8 from number 2. And so 8 times 0.8 gives us a new rate of 6.4, which matches what we got right there. Okay. Alright, so congratulations. Thanks for sticking around for day 1 here. And so in this lesson we learned how to write a rate law. We learned what a rate constant is. It's a unique constant for a reaction. It depends only on the reaction and the temperature which you do the reaction. And then we also learned what an order was. It's an exponent, either 0, 1, or 2. That tells you how the rate depends on the concentration. You put all that together, you get the rate law, which allows you to calculate the rate at any concentration. Math is pretty simple. The ideas aren't that much more challenging, so hopefully you're ready to try out the online homework now. Okay, thanks, and we'll see you around. Hang in there and stay well. Our concentration is to the first power